What if I told you that the same elements that power nuclear submarines also help detect smoke in your living room? That's right. Welcome to the mysterious and powerful world of the actinoids. This family of 15 elements, starting from actinium with atomic number 89 to lawrencium with atomic number 103, forms the second row of the F-block elements. Just like their lanthanoid cousins, actinoids are positioned beneath the main body of the periodic table. But what sets them apart? Their radioactivity. While a few actinoids like uranium and thorium occur naturally, most of them, especially those beyond uranium, are man-made in laboratories or nuclear reactors. And though they're often hidden in textbooks and charts, their real-world presence is immense, from nuclear fuel rods to cancer treatments and even smoke alarms. So let's pull back the curtain and uncover the chemistry of this powerful and reactive series. Let's zoom in a bit closer and examine their electrons. Actinoids fill the 5f orbitals and their general electronic configuration is written as Redon core 5f1 to 14, 60 0 to 1, 7s2. But here's the twist, these 5f electrons are poorly shielded, which means they feel a stronger nuclear pull and participate more in bonding. That's why, unlike the lanthanoids, actinoids exhibit a wide range of oxidation states. While the +3 state is common across the series, elements like uranium can show +4, +5, and even +6, for example, in the uranyl ion, written as UO2 with a 2+ charge. Neptunium and plutonium go even further, showing states up to +7. This variation arises due to the comparable energies of the 5f, 60, and 7s orbitals. These shifting oxidation states not only make actinoids chemically fascinating but also central to redox-based nuclear processes. When it comes to reactivity, actinoids are bold and aggressive. They're all metals, typically silver-white in appearance, but don't expect them to stay shiny for long. They tarnish rapidly when exposed to air due to surface oxidation. Drop one into an acid, and you'll see a rapid reaction with hydrogen gas being liberated. For example, M plus 6 HCl gives MCl3 plus 3 H2 gas. That's a basic acid-metal reaction. Their electropositive nature makes them highly reactive, especially in finely divided form. Additionally, in higher oxidation states, they form stable complexes, a property that's especially useful in nuclear waste treatment and actinide separation. Their tendency to form oxides, halides, and organometallic compounds makes them versatile players in high-energy chemistry and advanced materials development. You might be wondering, how do actinoids compare with lanthanoids? While both series involve F-block elements, the chemistry of actinoids is far more complex. First, they involve filling of 5 f-orbitals, whereas lanthanoids fill 4f. But the real difference lies in how these orbitals behave. The 5 f-orbitals in actinoids are less shielded and extend further from the nucleus, allowing them to engage more actively in bonding. That's why actinoids exhibit variable oxidation states, from +3 to +7, while lanthanoids mostly stick to +3. Also, most actinoids are radioactive, whereas lanthanoids are relatively stable. In fact, this radioactive property defines how actinoids are handled, often under strict conditions with specialized containment. Their magnetic, optical, and chemical behaviors make them more exotic and harder to predict compared to the lanthanoids. Let's now discuss a subtle but important trend, actinoid contraction. Just like we saw in lanthanoids, actinoid elements also show a steady decrease in the size of their ions as we move across the series. This happens because the 5f electrons poorly shield each other, causing the nucleus to pull the electrons closer. As a result, the ionic radius of actinoid 3+ ions, written as M3+, decreases gradually from thorium to lawrencium. This contraction affects their chemical reactivity and makes the separation of actinoids, especially in mixtures, a tough job. Chemists often rely on advanced ion exchange and solvent extraction techniques to isolate individual elements. If you plot atomic number on the x-axis and ionic radius on the y-axis, you'll notice a smooth downward trend, one that reflects the subtle interplay of nuclear charge and electron shielding across the series. Let's bring this all back to the real world. The actinoids are not just theoretical wonders. They're central to some of the most powerful technologies on Earth. Uranium-235 and plutonium-239 are the cornerstones of nuclear energy and nuclear weaponry. Their controlled fission reactions release immense energy used in reactors that power cities and submarines. Americium is found in household smoke detectors, acting as a reliable radiation source. Elements like thorium and isotopes of uranium are being studied for targeted cancer treatments and radiotherapy. In space exploration, curium and plutonium are used in radioisotope thermoelectric generators, the devices that power probes like Voyager and Curiosity on Mars. Their ability to release consistent energy over long durations makes actinoids the heart of modern science, energy, and defense systems. Let's quickly revise what we've explored about the actinoids. These 15 F-block elements stretch from actinium to lawrencium and feature the filling of 5 f-orbitals. They stand out for their radioactive nature, wide-ranging oxidation states, and high chemical reactivity. While the +3 state is common, many actinoids explore higher states, especially uranium, plutonium, and neptunium. Actinoid contraction, the gradual shrinking of ionic size across the series, affects their separation and bonding tendencies. From powering nuclear submarines to detecting smoke and treating cancer, the actinoids are deeply embedded in critical technologies of the 21st century. Their chemistry might be hidden behind thick lead walls and protective gear, but their impact radiates across medicine, energy, space, and defense. I hope this session helped you appreciate the silent strength and chemical complexity of the actinoids. They're not just elements, they're engines of innovation. Until next time, keep exploring the periodic table, where every block has a story to tell.